Good morning, participants, and welcome to our Texas Instruments webinar for this morning. Specialist Mathematics, What's New in 2016, as everybody awaits to see. Preparing for next year with our new Australian curriculum courses. What are the changes? What are some clever ideas that we can use to embrace the new parts of the course? Our presenters for today are Ray Rosen and Peter Fox, and just before I tell you a little bit more about them, I am sharing with you my desktop, which is the PowerPoint that you've been viewing while you've been waiting for the webinar to start. There's a couple of things I would like to point out, especially the opportunity to ask questions. You will notice in your WebEx software that you have the opportunity to have a chat window and questions. Can I ask that when you send a chat, can either be through Q&A or chat, can I ask that you send it to all panelists, please? That way I get a copy as well as our presenters, and we will do our best to try and answer your questions as we go. We do encourage the questions, and we're even thinking, because this is a 90-minute presentation this morning, we are looking to stop possibly, or pause possibly about halfway through to just to round up any questions that might still be outstanding and have our presenters the opportunity to respond to questions. So there'll be a mix of us responding to questions as we go, or doing a bit of a roundup at half time, and then of course again at the end. So that's the chat. And just another one on the sound. If your sound does drop out, if it's not working on your computer for whatever reason, you can also log in through the telephone. So that's the phone number, the 1-800 number, and you'd need to check with your email, or in the WebEx, there's a window you can open to check your meeting number and attendee number that you would be asked for on the telephone. So moving on to introduce our presenters for today, you're firstly going to be hearing from Peter Fox. Now, Peter's an absolute gun with the materials that he prepares and presents. I've been to quite a few of Peter's presentations and always gone away with clever ideas and also feeling invigorated from Peter's entertaining presentation style. Now, Peter, at the moment, is working with Texas Instruments, but he's not very long out of the classroom, and I remember stealing some of his teaching ideas when he was still teaching. He's been doing that for about 20 years. He's also done work with the universities of Melbourne and Monash and the VCE. So Peter will be talking to us first, and following that we get Ray Rosen. Now, Ray at the moment is a senior educator at RMIT, teaching a mix of maths methods, specialist maths, and also subjects in the Associate Diploma of Engineering. He has worked with the Victorian Curriculum Assessment Board and also co-author of the maths text, the specialist maths text that I'm currently using with my class, Ray. So thanks for that, and I'm finding that quite good. So without further ado, I will switch you across to Peter.
Thank you, Brian. Let me just share my desktop.
Now, Peter and Ray have already had a bit of a go at this on Monday this week. They did a live presentation day at Mount Waverley Secondary College.
Now, I'm assuming you can see my desktop now. The very first thing that I wanted to talk about was the fact that the Unit 1 and 2, Specialist Maths, and a lot of people would be aware of those changes, at least in terms of the title changes, and that previously, or the current course, if you like, for General Maths, it's a very flexible study where teachers can draw upon material relevant for further methods or specialist. But the difference was that everybody was recognised as doing the same general mathematics course. And that's the reasoning, if you like, behind the introduction of Specialist Maths Unit 1 and 2. So the new course is a lot more prescriptive. It has some required areas that need to be completed. and it's designed specifically to prepare students for studies in Units 3 and 4. Now, having said that, is that none of the material that's covered in that course can be examined because it's not a prerequisite. So students shouldn't expect to see exam-type questions based specifically on Unit 1 and 2. So an area that I would think of there is proof by induction, for example, is included in Unit 1 and 2. I think that provides a good opportunity to strengthen students' algebraic skills and perhaps help them think about proof for vectors, but it can't be examined specifically in Unit 3 and 4. I had clarification of that from the VCAA, is that only the things prescribed in the actual study design itself on Unit 3 and 4 are the sorts of things that can be examined. So the current specialist course, Unit 3 and 4, there hasn't really been a lot of changes in the last 12 years except for the inclusion of CAS, of course, which is, I guess, fairly significant, but the structural changes really amounted to dropping out some of the old elective material and having a fully prescribed course. So the new course is fully prescribed. There's some significant changes, as people are aware, and Raymond and I will cover the examples of that, and I think the elephant in the room would probably be the statistics. And don't look forward to it being pulled out, although a lot of people have said they'd love to see it taken out. My understanding is it's there to stay, and certainly a lot of high-level maths courses around the country include some level of statistics in their courses. So it's new to Victoria, but it's certainly not new to all states to have stats in this level course. So one thing that I've suggested to people when I did some of the regional PD events was that they read the new study design in isolation, pick up the old one and basically hide it away in a cupboard. You don't need it at the end of this year. And therefore just look at the new study design. And one of the reasons why I suggest people do that is because this sort of thing can happen. And if we look at that, most people will read it as once in a lifetime, but of course it's like the old one, Paris in the spring, is that you miss some of the subtleties, and that's what I said before, is that there's some subtleties that occur. And here's an example of one. Anti-differentiation using partial fractions of rational functions. I've put the reference to the study design there on page 83, and it would be very easy to say, yep, that's what was in the course before. But there used to be a comma that included reference to with quadratic denominators. Now Raymond's going to give us some examples of some calculus type stuff with rational functions and so on later on in this session, and how you might do that using the calculator. But certainly there's a subtle difference. There is, we're no longer restricted to quadratic denominators. So if you start to write down questions for that sort of problem without that wording there, you'll see that you can include a lot more. So as an example, that one is still in and is currently in because it has a quadratic denominator. And it's under the new course under the heading rational function. This one would be in the current course and the new course. It fits the description above. And that one in the current course would have been by substitution, even though it's not a quadratic denominator. It would pass as a substitution. Passes in the new course because it's a rational function. This one, however, in 2016, but wouldn't be in the 2015 course because of the restriction being a quadratic denominator, and the other methods would be used to do that by hand, but would be included in the new course. But I think if anyone sat down and tried to do that by hand, they would see that it would take a lot of time, so it would have to be a fairly highly scaffolded question if that were the case. Another one, which is relatively subtle but significant in the number of exclusions, I'll call it, is that the use of the Argand diagram to represent points, lines, rays and circles, and people would read that and go, yes, that was in there before, but previously we had ellipses and hyperbola specifically mentioned there. They're not mentioned anymore, nor are regions. So, for example, the absolute value of z equals 3, that would have been in the old course, still in the new course under the definition of circle, so that's okay. This one here, that would be in the 2016 course and the 2000 or the current course, because it comes under our reference to a line in the complex plane. And this one here, no longer in, which I actually find a little bit disappointing because of the fact that if you look through the Unit 1 and 2, they do actually look into conic sections. And a geometric understanding of that problem, an ellipse being the sum of those distances from the two foci being constant, it's a lovely way to treat it. So I'm a little bit disappointed that it's not in the course, but that's the reality. Based on the description, page 82 of the new study design, it's no longer in. So ellipse currently in, but not for 2016 and beyond. Another example, absolute value of z less than 3, no longer in. I don't think that's significant in terms of the amount of work people were doing on it, but it is significant in terms of the fact that you can no longer be asked to do a region. And one little tip that I would give people is if you want to check a specific word, Control F in the study design is a nice thing. It's a find, and you just type in the word and it will zoom through the whole study design and see where that word occurs. And if you do that, you'll find words like proof, for example, now occur about 10 times more frequently as what they used to, and the word region is no longer in Unit 3 and 4. Other ones, small ones, absolute value function. I think most specialist teachers would have assumed students knew it because it was in mathematical methods. It's been bumped across into specialist. And from memory, I don't think it's in the methods course. But if you're watching our other webinar, you're a glutton for punishment today, 3 hours of webinars, there's a webinar on methods, what's in and what's out. Graphs of rational functions of low degree. I find that one interesting because we've not defined what a low degree is. I have friends that live in Darwin. My daughter's currently in Darwin on a school camp, and low degrees would be 30 degrees for them, but not here in Melbourne, in Victoria. So low degree, it's, I guess, open to interpretation, and I think it's just a matter of people being pragmatic or logical about what sort of things people would be required to do by hand. It's less prescriptive, mainly because of the fact that with the use of CAS, we can crank things up a bit if we need to. Their asymptotic behaviour and locations of stationary points and the like. Another one that's in, and there's a few questions people might like to ask, is concavity. So we've got a continuous function whose value at the midpoint of every interval in its domain. I don't think that's the definition that people will be using. I think it's more likely this latter one, because if it's a continuous function, a necessary and sufficient condition is that the derivative be greater than 0 for all points in the interval A to B. And given that our students are required to know the workings behind the second derivative, then that's a reasonable definition, I think, for students to be using, or teachers in this case. So that's a quick run through of the sorts of things that are in and out. It's not complete. There's a few more things that Raymond and I will go through. But the other thing I wanted to mention before I hand over to Raymond to give us some examples on how to use Nspire to solve some of these problems. Circles on a complex plane is an activity that I've put up just recently, and you'll find it's got this lovely little checker plate thing here, and if you're not sure what that's called, it's a QR code. And what we're finding is that almost 50% of the searches on the internet occur from mobile devices. I think that's largely an impact of the younger generation, because I still use my desktop computer to do a search most of the time. But the students can use a QR scanner on their phone. It's a free app that you can put on most smartphones, and if they're doing this worksheet and they're not quite getting the understanding, or they might be looking for another question, or they might be looking for their teacher might be away and the teacher might have given this as a worksheet for the students to do in their absence. So the student can just scan that with their phone. It takes them straight to a video which we've put up on the internet, on YouTube, and it goes through a complete explanation of circles on the complex plane. It gives them 3 levels. First part is an understanding of what's going on, so delivering a concept. The second part it looks at is a sample question, and then the third part that it looks at is how you would do that on the Nspire calculator. In addition to it, and I guess a subset of the above 3, is it then says, here, try this question. So it makes sure that students are not just listening, that they're actually doing as well. So they can do the question, and it says, now pause the video, and they pause it and try the question, and as soon as they resume the video, it provides an answer for them. So they're the sorts of worksheets that we're putting up, and you can see this one is similar to the other sorts of documents everywhere else, where it has calculator instructions and there's some questions in there. And the beauty of it for teachers is that we have a second document, a companion document that goes with each of these, which has the answers on it. And of course they're all free for teachers to download. So hopefully that gives you some idea of the sorts of materials that are being prepared. So certainly watching the webinar is a good start. And the second thing to do will be jump on our website, and by the time the MAV conference comes around, we will have a separate section on our website for people to look at, which is just for the senior curriculum. That's a big job because of the fact that it's different in every single state. But these files are already on our website, but they're in something called the Activity Exchange or Learning Centre, and you have to go through and find them for yourself, whereas by end of this year and certainly the start of next year, you'll be able to just go in and click on Victoria, Specialist Maths, Unit 3 and 4, and then look by area of study and pick out your activities. There's tests there, which I'm delighted to say Raymond has written a lot of those. We've had to modify them recently because of these changes. So there's automated tests. You can have them as a PDF, an Nspire file or whatever, and lots of these activities and videos. So without further ado, what I'm going to do is transfer over to Raymond, and he will provide us some examples on how to use TI-Nspire for or on the CAS. So it's over to you, Raymond.
Yes, hello. Hopefully everybody can hear me. Good morning. So this morning what I want to do is just to work through a couple of worked examples on the TI-Nspire. Now I presume everyone can see my desktop here. What we're doing is intersections and drawing some points and some curves on the Argand plane. Notice specifically that we're restricted now to circles, lines and rays. Okay, no more regions are to be sketched. No colouring in the areas or finding the sectors or the segments. However, I still feel that we can find the intersection, if you look at part 2 there, between S and T, so finding the intersection between, say, a line and a circle, or between a ray and a circle, because the intersection is in fact a point. For example, a curve, a circle and a straight line may intersect at 2 points, they may intersect at 1 point, they may not intersect at all.
Ray,
so basically what we're going to do here is show how TI-Nspire can use these.
I haven't seen your desktop yet. I don't know
whether sorry to interrupt.
Slow.
Yeah.
I can't
We're
see
not seeing the desktop, Ray.
Okay, do I have to share?
Yeah.
Okay.
So
all right, share my desktop.
The shortcut there, that's it.
Yep.
Beautiful.
You got it now?
Yep.
It's looking good. It's on its way. We were imagining all that anyway, Ray.
Well,
we
that's
had
right. Imaginary numbers, we can do that.
That's right. Imaginary numbers, imaginary desktops. That works.
Okay.
We've got it now, mate.
Got it now? Right.
Yep.
Okay, so what we've got here is sets of points in the Argand plane. First of all, the region S, mod Z plus 3 plus I equals 5. The region, or the set of points T, Z, arg Z plus 3 equals minus 3 pi on 4. And R, mod Z equals mod Z plus 3 plus 3I. So what I want to do is I want to show you basically how we can use TI-Nspire to find the Cartesian coordinates of these sets of points. Okay, so we'll do all this on a calculator page. We could do this on a notes page. The first thing we really want to do is to define Z to equal X plus Y times I. Now, we probably don't need the multiply sign in there, but I think it's a good choice that we always do put it in. And also make sure that when you use the complex number I, you are actually using this I, not just the letter I. Okay, so that's the first thing we have to do. All right, now, we want the first one was the circle, or at least we know it's a circle, so let's try and get its equation, which was mod z. We could type in abs, but I think we'll just get the abs, or the absolute value from that template there, and type in z plus 3 plus I equals 5. Now, we've just come up with that equation. It'd be nice if we could sort of square both sides of that equation. So if we want to just type in some arrows there, up arrows, and now square both sides, and we now come up with that. Now that's the circle form in the completing the square form. It would be nice if we could complete the square, and that's in fact what we want to do now. We will complete the square. So we'll go Menu, Algebra, complete the square on that equation. So just press the up arrow. But I want to complete the square on both the x and the y. And having done that, that gives me now the circle in the completing the square form, and we can see that the centre of the circle is -3, 1, and it has -3, -1, and it has a radius of 5. Okay, so that's the circle, standard form of the circle. If we look at the second example here, arg z plus 3 equals -3 pi on 4. We can actually obtain the Cartesian form of that. Now, to get that one, although the arg, what does the calculator call arg? The arg is under complex number tools. So complex number tools, and here we want the polar angle. So the polar angle is what the calculator calls angle, is what we're calling arg. So arg of z equals -3 times pi on 4. Now another little note here is that we can actually just type in pi if we get lazy. So -3 pi on 4. Now that's not quite what we want, so we can use the algebra command again, or just type in solve. So we want to solve that equation for y. So having done that, that actually gives me the Cartesian form, but note carefully that it gives me the restricted domain there of x less than -3. Strictly less than -3 because the point -3 is not included there. Now geometrically, what is this point? Well, this point is the point from the point -3 making an angle of -3 pi on 4 with the real axis. So it is just a ray. Going back to the circle again was just a set of points from the centre which are all equidistant 5 from the circle, all the points on the circumference of the circle. All right, now the last one that we were looking at there is R. R, well, this one is the set of points which are equidistant from the origin to the point -3, -3i, or the point -3, -3. So let's try and find out what this one is in the argand plane as well. So once again, we'll type in the modulus of z equal to the modulus, this time, of z plus 3 plus 3i. Okay, once again, we need to square both sides. We could just square the answer. Alternatively, we'll just square both sides. Now, it hasn't cancelled out the x squared plus y squareds on both sides, but no problems. Once again, we'll just solve this equation for y. And this time we've got y equals -x minus 3, which is a straight line. Okay, now, having got the Cartesian forms of these, the next part of the question was, in fact, to sketch them. I'll sketch them in a moment, but now what we want to do is we want to find the points of intersection between S and T, or between S and R. So let's come back and solve, basically, as a simultaneous equation. First of all, I'll want to solve, what am I solving? I'm solving the equation of the circle. So we can say solve. Now, where was the circle? I'll just go up and grab the circle. Solve that, space, and what was the straight line? I'll type in the straight line, the argument. So it was this one. I don't want the and in there. So I want to solve that for x and y. but I have to give the restriction here that x was less than minus 3. I have to get rid of that. Okay, so what's going wrong here? Solve that expression for x and y given that x was less than minus 3. So there we've got the points of intersection. Now, another way we can actually do a lot of these intersection between circles and straight lines is to use the zeros command. Now, the zeros command is a little bit trickier. So we can get the zeros command from the algebra menu, but the zeros command has to have now a template. Now, the template is this little template here. Now, when we solve for the zeros it's got to be equal to 0. So we're not going to type in the equation equals 0. We have to just type in the equation as though it was equal to 0. So to do this for the circle, it was just the modulus of z plus 3 plus I, but then it's got to be minus 5 because that's where it's equal to 0. The same thing for the ray was angle z plus 3. It was equal to 3 pi on 4, so now I have to say plus 3 times pi over 4. And then once again, we just go comma x, comma y. And that will then also give me the solution set. Notice that it gives it to me in forms of a matrix there, minus 7, 4. So you have to realise that the solution there is x equal to minus 7, y equal to minus 4. So we've actually found the solution between the circle and the ray there without actually obtaining the equations or the Cartesian equations for those two sets of points. So using the zeros command is very, very nice there. All right. Now, we could also find the second one, and I've already got this one prepared, so we'll show you what happens here and show you the graph. So there's the solution there, and there's the solution for the second one. The second one then is the solution, I'm not typing it all in, you can see it on the screen there, for the straight line and the circle. Once again, we can type this in a number of ways. The equation of that line, mod z minus mod z plus 3 plus I, is also the line real part of z plus the imaginary part of z plus 3 equals 0. So we can also see that the equations for lines are not necessarily unique. The same thing can also occur in parametric equations for vectors, where the parametric equation for a vector is not necessarily, for a graph is not necessarily unique. There is more than one form. And algebraically, what does this represent? The set of points from the point minus 3 to the origin being the equidistant of all those points. All right, so let's have a look at this graphically now. Sorry. So we've got the circle in green. The circle is the set of points equidistant from the centre to all the points on the circle. We've got the ray here, which is just the point from the point minus 3, 0, going down, making an angle of minus 3 pi on 4, and that straight line, the red straight line there, intersecting the circle at the 2 points that we saw as well. So notice also another nice little neat way of describing these graphs is with the zeros command as well. A number of ways we could actually do this. We could type it in as the zeros command. Remember the zeros command, you don't say equal to 0, you just type in the zeros of the function, comma y. Why y? Well, that's just the syntax for this. Also, another idea that I've just recently thought of to do all this is that why not actually just define these functions or these variables? If I define s to be assigned equal to z plus 3 minus 5, t to be the ray, and r to be the straight line, then we could just type it in directly as this and get the points directly. Saves a little bit of typing, and not only that, when I've defined these z, r and t, I can just also type them in directly into the equations there. So the zeros command is a very, very useful one for not only plotting the graphs, but also for solving the solutions between the straight line and the arc or the ray or the circle with the straight line as well. So just remember now, when we're talking about complex numbers, we only have to talk about circles, lines and rays, or intersections between rays and circles and lines. All right, so I think that's probably enough with complex numbers. We have a lot we want to get through today. So what I will do now is move over to another...
Just before you do, Ray, there was a lovely question came in on the chat. If you could just jump back to that example you're doing on complex numbers. The one that was interesting is someone had asked, I think it was Bajana actually, said, can you actually store those equations? And I thought that was pretty good because you can, rather than having to type them all, so if you've got something like the absolute value of z minus 2I equals 3 or something, you can actually store that as equation 1. And therefore you can then say things like solve equation 1 and equation 2 and pull them up from your variables menu in that way. And it makes it a lot quicker to type. Certainly it's easier to type on the calculator and copy and paste, but I thought that's a good idea. I hadn't done that before. So, yeah, you can type in equation 1 and then assign it equal to one of those ones that you've got, and then just solve for S, solve for, like you've got there, solve.
Like I've got here.
For S and R, I thought that was pretty good.
When I've got these, though, I've got S and T and R not equal to 0, well, it's assumed equal to 0, so therefore I'm using the zeros command here. But what you're saying is that I have to have an equation. I often do EQ1 or EQ2. EQ1 is, say, assigned equal to, and let's just grab the first one. But now I'd have to say that is equal to 5.
That's right, yeah. And I thought that was good because they can then say solve equation 1 and equation 2. It's a very generic thing to do, and it's a literal thing to do as well, I guess.
Oh, equal to minus 3 pi on 4.
Yep.
Yeah, so then we're just going to go solve, and we don't even need to press it. We just get the variable from the var command, EQ1 and EQ2, comma, X, comma, Y. That should work. No, it didn't.
It's a comma instead, that's it.
There we go. So that's another way of doing it as well. So yeah, to avoid your typing, you can just assign equations. But notice the equations in the solve command must be an equation equals, whereas storing them when we're using the zeros command, they're assumed equal to 0. That's the tricky part there. All right, so that's some good little ideas. I only thought of storing them the other day when I thought about doing these sort of questions, saving a bit of typing. All right, so let's have a look at, sorry for scrolling through all this stuff. Let's have a look at one of the equations now, which is sketching some graphs. No, sorry, we'll get to the right parts here. Okay. Where are we? All right, what we want to do is we want to sketch a graph now. Now, let me just, find the right graph that we're looking for.
What Raymond's doing, if people haven't seen that before, is if you use Control and Up arrow on the calculator, Raymond's document's very large, but it does allow students to navigate to the point that they want. You may have noticed that it says 2.1 at the top, so that's problem number 2, which means there's a break in any variables between problem 1 and problem 2, which is very handy if they're doing these large documents like what Raymond's got.
All right, now Peter was talking about for sketching graphs. Previously we've sort of sketched graphs of the form what y equals ax to the m plus bx to the minus m, where m and n are sort of -1 or 1 and 2. Here we're actually sketching rational functions of low degree. Now I will assume here a low degree is a quadratic divided by a quadratic. So we want to sketch the graph of this equation. Now, of course, we can just go straight to the graphs page and sketch it. But, of course, we actually have to obtain the coordinates of the x-intercepts, the y-intercepts, the asymptotes and things like that. So what I'll do now is show you how we can actually get some of these little ideas. So, first of all, whenever we're doing something with a function, we can just define a function, and I just type in define because it's very easy to get. Alternatively, we can just get it from menu actions define, and I will define my function f1 of x to equal the function, what is it? It's 2x squared plus 7 times x minus 4 over x squared plus 2x plus 3. So always remember to get out of that power by pressing the arrow. Okay, now another little idea that people like in interactive documents is an idea that sometimes when I want to type some information in, but I don't want the calculator to actually evaluate it. So what we can also do from this actions command here is number 6, insert a comment. So if I go insert a comment, you see that little comment symbol there, and I can just type in, say, crosses the y-axis when x equals 0. And that's not interpreted by the computer there or the TI-Nspire software. So that's a nice little idea just to have some sort of extra information on a page there. So if I want to find the coordinates or the y value where it crosses the y-axis, just type in f1 of 0. And that'll give me what y equals 4 on 3 when x equals 0. Alternatively now, well, I just want to find where it crosses the x-axis when y equals 0. So just typing that up in again. You don't have to type it all in again. You can just edit your expressions that I just did then. So this time we want to solve when the numerator is 0. Well, solving when the numerator is 0 is effectively just solving the function equals 0 anyway. So that will just give me x equals minus 4 on 3. X equals minus 4 and y equals a half, which is effectively exactly the same as if I looked at the factor of f1 of x. So when the numerator is 0, that's when the graph crosses the x-axis. When the denominator is 0, we can see that the denominator is 0 when x equals 1 or x equals minus 3. But what a lot of people would like to be able to get is to extract the denominator from that function f1 there. So we can actually do that. So this is one that's not actually well known as well, some little features here. If I go Menu and Algebra and Fractional Tools number 9. In the Fractional Tools here you see Proper Fraction, Get Numerator, Get Denominator and Common Denominator. So what we want to do here is actually to get the denominator. So if I just get the denominator of f1 of x, then that's just extracted the denominator, and then we can just say solve when the denominator is equal to 0 for x. So that gives me the vertical asymptotes. Now, the vertical asymptotes are x equals minus 3 and x equals 1. Now, we also want to obtain the horizontal asymptotes here. So again, we might just put in a nice little comment here. So actions, insert comment, say HA. Nice shorthand for horizontal asymptotes. To obtain the horizontal asymptotes, we actually have to do a long division process to divide the denominator into the numerator. But that can also be done from the fractional tools. The fractional tools there were proper fraction. So let's just get f1 of x into the proper fraction form, and we see that it divides in 2 plus 3x plus 2 over x squared plus 2x minus 3. So in fact the line y equals 2 is going to be a vertical asymptote. We can also perhaps get that from the limit as x approaches infinity. So let's just try that one and thought of that one. The limit as x approaches infinity, either plus or minus infinity. We don't need it from above or below of f1 of x. Sure enough, it's 2. So the line y equals 2 is a horizontal asymptote. Now, if we were to ask lots of people what is an asymptote, I'm sure we get the answer. An asymptote is a line which is never crossed. Well, that's not quite true. Vertical asymptotes definitely are never crossed, but horizontal asymptotes are crossed. We can see that in fact y has the value of 2 when the numerator here, 3x plus 2, is equal to 0. So if I extracted the numerator from there, or alternatively, if I was just to solve, we can just type this in, 3 times x plus 2 equals 0 for x, we'd see that x equals minus 2 on 3. So when x equals minus 2 on 3, yes, this curve does cross the horizontal asymptote. And that's a new little feature that people are probably not aware of. Perhaps we should also check this function for turning points. So for turning points, we want to differentiate it. So once again, I could get this from the calculus menu, but I love this little template. It's got most of the things we need on it. So d by dx of f1 of x. And, well, what I want to do is I want to solve and want to see where the derivative is equal to 0. I could grab that one there, but I might as well do a more generic sort of formula and try to solve for that equal to 0. Equal to 0 for x. False. Well, what does that mean? That means that there are no values for x for which the gradient is 0, which effectively means that there are no turning points of this graph. All right, so if we just scroll across and have a look at the graph already prepared, we can see that x equals -1 is a vertical asymptote which is approached. X equals -3 is a vertical asymptote. The line y equals 2 is my horizontal asymptote. And in fact, the graph crosses the horizontal asymptote at the point -2/3 and 2. Also note that we can draw these vertical asymptotes, x equals 1 and x equals -3. They would not be included when I just sketch the graph of the function. And we can also change the attributes of these graphs to get the asymptotes dotted. So, for example, when I highlight the asymptotes and the control menu attributes, we can have the line weight thin, thick, medium, or we can have them dash style or dotted or whatever we like. So that's a nice little feature to include the asymptotes as a dotted or dashed line as they're meant to be, and also to change the colour with the attributes to show that the asymptotes are different from the actual graph. Because remember, the asymptotes are not necessarily included when we sketch the graph, so we should incorporate them as well. All right, so that's another little new feature that's definitely in the Specialist Maths course when we start sketching these graphs which can cross horizontal asymptotes. We've also looked at the complex numbers. All right, Peter, is there anything else you want to go, or we'll go on to the arc length since we haven't got a lot of time?
Yeah, I can do the, well, no, you do the arc length one. Or actually, just before you do the arc length one, did you want to drop across to me and I'll give them a demonstration? We mentioned before that concavity is in there, and I think that's probably a good one to include.
Okay.
Let me just share my desktop. We'll play Desktop Lotto for a second and see which application it jumps to. Oh, there we go. Good choice. So
pick an application.
Yes, that's right. So hopefully you're seeing that now is concavity we mentioned. So this is another activity which we will be putting up later on. And a nice little question you could ask students is determine the conditions necessary for b and the function x minus b, x minus a rather, x minus b, x minus c, as it says written there, to be convex or concave up over the interval from 0 to 1. Now, there's a question you might like to send through, not to me, but perhaps to VCAR, because what we probably should have mentioned at the start is Raymond and I don't work for VCAR, as Brian showed us at the start. We're teachers or have been teachers in my case, and the thing that Raymond and I share in common other than a love of Inspire is the fact that we've both written content, so therefore for these new courses, and have therefore read over this study design a lot. But what you're seeing is our interpretation of some of these things. Some of them are fairly explicit. I would like to know, just personally, do students need to know convex, or would they prefer to see the words concave up? Or should they be bilingual and be able to tackle both of those? Because most of the textbooks I've seen written, Raymond, in your textbook, do you refer to it as being convex or concave up?
Yes, not really sure about that one. It's convex and concave just really mentioned sort of very briefly. You know, I'm not really sure how these concepts are going to be examined, perhaps in just a multiple choice type question, or just to basically find where the second derivative is positive or negative perhaps. But it's going to be a tricky one to see how these are going to be examined.
So, I'm interested to see where the wording, because I think wording could throw students off in an exam, and that's obviously why a lot of us are here, is thinking about what sort of things are going to be on the exam. So here's a sample of a question where we have A, B and C as parameters, and we want to know how would we look at this solution. So points A, B and C on this page are flexible, so therefore we can move them around. And what I've done, just to make the question a little bit more interactive, the little note down the bottom tells us that this is currently concave, and if I move it around, it's neither concave or convex over the region from 0 to 1, but now it is convex. So it's a question for students to try and figure out what are the conditions necessary for the region 0 to 1, what are the conditions necessary for B for this to be convex. Now, if you're wondering how I've put that little red line in there, what I've done is actually graphed two functions. One is the original one, f1 of x, and the red one is just over that restricted domain, and then you can make it a little bit thicker and so on. So that's how I've managed to just highlight that region. So that's an example of a question I think would be reasonable for students to have to answer. And then what I did, just to have another look at that question, is said, well, let's draw a graph of the second derivative, because that's what we'd most likely be using as our test for concavity. And you can see here, this is the graph of our second derivative. This is the region for which we're interested in. And therefore, as I change my function, just moving my a's and b's around, we can decide whether the region is, in fact, concave, convex. The second derivative needs to be greater than 0. So now you can see this region here, which is the graph of our second derivative, is now all positive. So I think that's a sample of a question. It's not necessarily one that might appear on an exam, but a sample of one students could use or teachers could use to explore the concept and make students focus on the second derivative. So it would amount simply to determination of the second derivative, in this case a linear function, and determine what conditions would be necessary for that linear function to kick off here, which really means that we don't really care about the slope of this thing, but we do care about its, let's say, its y-intercept. Yeah. So there's an example of how you might look at concavity. And we've got a worksheet or an activity that's going to come up on that one.
Yeah, I quite like that, Peter, particularly emphasising the connection to the calculus.
Yeah, the fact that it's graphing the second derivative, people want to see how you can graph that second derivative. That's simply it there. You've got your function in f1, and then you just tell it to graph the second derivative of f1, so it becomes dynamic. And I think that's a nice way for students to interact with the graph and see it. And these points here are simply, I just picked up their coordinates, and that says that's A, that one's B, and that one's C. So that's the A, B, and C here. So if we go back and have a look up at f1, it's just x minus, I'd just divide it by 12 to dilate a little bit, and that's it. So it makes it interactive. So yes, while we're on that functions and calculus sort of area, the algebra area of study, or sorry, functions and graphs area of study, I thought I might just throw that one in. So let me just transfer back to Raymond.
So guys, we're about at our halfway mark, and there's been a few questions that have come in, but we've discussed those already. But please, can I encourage you, if you do have any questions to the presenters while we're going along, please type them into either the chat or the Q&A window, and direct it to all panellists.
All right, you can see my desktop now? Yep. Okay, we'll just quickly go through the differential equations and get on to arc length. Specifically mentioned now in the syllabus is the differential equation of what I call type 3 differential equations, which is dy dx as a function of x times a function of y. Previously, we've had sort of the type 1 when the g of y is not there, and type 2 when the f of x is not there. But this time, specifically mentioned, is this type 3 dy dx as f of x times g of y. So this is a case where we can actually separate the variables and get all the y's on one side and all the x's on the other side. So some specific examples of this are, say, f of xy equals x plus 4 over y squared plus 4. Now, the DE solve that we've used in the past will also work with this type 3. So DE solve y dashed. If you want to get the dash, you have to get it from the little template on the side here. So we've gone through this one before. But one thing to note is that often when we get a general solution involving these situations, often the solution will be given as what's called an implicit relationship. In some cases, such as these, it is not physically possible to rearrange to make y the subject. Also note that we're going to have integrals on both sides of the equation, But really we only need one constant because it's a first order differential equation, so we only need one constant on one side of the equation there. In some cases, or when we have a particular solution, so we've got the extra information, y of x0 equals y0, in some particular cases it may be possible to rearrange to make y the subject. So in this situation, dy dx plus y equals 6x squared y, with the initial condition y of 2 is 1. In this case, it is possible to rearrange to make y the subject. Other times when we're solving differential equations such as these, we might be interested in saying for what values of x is this solution valid. So a solution here, for example, root 16 minus y squared, y is restricted to be between minus 4 and 4. We'll get a solution here and we'll get an implied domain restriction in these differential equations. So often it is important to specify the domain for when these solutions are valid. All right, so as I said, this type is specifically mentioned now in the syllabus, so we have to be really careful with solving differential equations like that. Second order differential equations, etc., are specifically there as well. All right, one of the other new areas of study, which I want to talk about now, is an arc length. Suppose we wanted to find the length of the curve. Arc length. This is the arc length. Y equals x squared from the origin, x equals 0, say to the point where x equals 2. We've previously used calculus to find, say, the area between two curves, the volume when the curve's been rotated around the x-axis or the y-axis, or in fact even the volume between, or the area between two curves has been rotated around the x or the y-axis as well. But another application of calculus now is arc length. Now we will get to the arc length formula, but before we get to the arc length formula, let's have a little think about how what we're actually doing for this arc length. So what I've done here is I've defined the function, say, x squared. So there's the whole of the function x squared, but this function here between 0 and 2, the line which is more solid there, I want to find that length. So I want to find the length of this curve. Well, one first idea that we could say originally is to say join the points at the origin, 0, 0, and join the point 2, 2, 2, 4, and find the length of that straight line segment as an approximation to the curve. Well, this can be done really quite nicely if we first of all define the function f of x to be x squared, and then all I've got here is a fancy formula for the distance between 2 points x1, x2. The distance between the points x1, x2 is just y2 minus y1 all squared plus x2 minus x1 all squared. And we calculate the distance 0, 2, or as an approximation 4.47. Now, first ideas was that straight line segment overestimating or underestimating the true length of the arc length or the measure along the curve there? In this case, it's an underestimate. So perhaps another idea would be, well, let's subdivide that interval into two smaller segments, from the origin to the point 1, 1, and then from the point 1, 1 to the point 2, 4. And let's try to calculate the length of these two blue straight line segments. Once again, we've got exactly the same as what we did before, defining the function, but this time I'm now working out the distance between the point 0, 1 and the point 1, 2. And we can see that it's getting sort of slightly larger. Well, all right, having subdivided into 2, let's try and subdivide it into 4 equal points now, 0 to 0.5, the x value 0.5 to 1, 1 to 1.5, and 1.5 to 2. And now let's try to calculate that length. Well, that length is the length from D, 0.5, 0.51, 1 to 1.5, and 2. And once again, it's getting a little bit bigger as well. I've rounded all these answers to 5 decimal places here. We could fix any number of decimal places. I've just happened to choose 5. All right, so this idea of subdividing, we've seen this before basically. What we're actually doing, if you think about when we found the area under a curve, we took the interval between A and B and subdivided into n equal sub-intervals, each of, say, of length h or delta x, and worked out the area of all the little rectangles. The same sort of idea is happening here. What we're really doing is now finding the length between all those little sub-intervals. So we can do this in a general situation now. And a general situation, this one's done on a notes page, to define the function, define the value of A, which was 0, the value of B, which is 2, The value of h I've just chosen to be a half, so in this case n would be equal to 4, and work out this formula. This looks pretty nasty. It took a bit of thinking to get this one done. But basically this is just summing all those little sub-intervals that we talked about before. And I've actually calculated this one with a slider for n. So for example, when n was equal to, say, 2, we got the answer that we had when we subdivided into 2. And when n is equal to 4, it actually comes up with the answer we had before for 4 as well. So a nice little investigation of arc length here I think is quite a nice idea. Basically, we can actually get a general formula for the arc length. It's a nice little hand-drawn thing. The arc length for any curve between A and B, well, if we just take any small sort of line segment there, any little line segment will be a line segment will be a straight line segment with delta x and height delta y. So the element of arc length is the limit as delta x approaches 0, the sum between x equals a and x equals b of delta x squared plus delta y squared, dividing through by the delta x all squared, taking out the common factor there of delta x, and as I said, from the limit of the sum, we know that's the definite integral. So the formula for the arc length is 1 plus dy dx all squared dx, or 1 plus f dash x all squared. Now, the problem is, though, is that most of the functions that we get for any function, even a simple curve like x squared or something, the integral that we're going to get here cannot be integrable by the integration techniques that we've got so far. So of course what we're going to do is use the calculator to find a numerical approximation to the integrals obtained. Another little thing I've got here I'll just quickly show you is actually an arc length program, because when I first saw arc length was coming into the course I thought it'd be nice to write a little program, demonstrate it on a notes page as well, but of course arc length with TI-Nspire is already an intrinsic or built-in function. So this is just a little program, and it's a simple little program. Display just displays things on the screen. Requests enters the values. You can actually request the function while the program is running and calculate the arc length. So as I said, the arc length, if you want to obtain the arc length is obtained from the calculus menu. So if we just go menu, if we're on a calculator page, if we're on a general calculator page and we just go menu to the calculus menu, and then down the bottom we've got tangent line, normal line, arc length. Now the arc length, if we had have got it from the catalogue or the book, we'd see that the arc length formula is very similar to what we do for the normal line or the tangent line, arc length, comma, 0, comma, a, comma, b. So you've got to go x there. Now the calculator actually gives us an exact answer there, because this one can be done, but if we want an approximation, we'll just press Control Enter. So arc length is a very nice new feature here. One other thing that perhaps we want to talk about here is to find the arc length of a curve defined parametrically as well, because this has actually been in the course previously, because the arc length is really just the integral of the velocity, and the velocity is just the norm or the magnitude of the speed here. So if we've got a particle moving along a curve defined by this, we can sketch the curve, find the speed, and find the total length of the curve as well. So to do this one, I've actually done this one on a notes page as well. So let me just go through this. If we just define x1 of t to be 2 cos t, define y1 of t as sine 2t, define then the position vector r of t to be x1 of t, y1 of t, we can define the velocity v of t to be the derivative of r of t, and this will calculate your velocity vector for you. We're not having the i's and j's there, but of course the i's and j's are assumed and students should type them in appropriately. But if we define the speed to be the norm, now norm is another command some of you may have seen before. Norm is just obtained from the menu command. Norm is just how the calculator interprets the magnitude or the absolute value of a vector. And the length is just the magnitude of the speed between the integral between 0 and 2 pi. And from that we can actually calculate the length of a curve in parametric form. And the length of the curve in parametric form is the total distance all the way around the curve that we're actually calculating from the point, say, t equals 0 to t equals 2 pi in this particular situation. Now, in the past, examiners have asked arc length. Arc length has been asked parametrically, but now we're restricted and have to find arc length also from a Cartesian curve as well. So we could also do an example where we could actually find the Cartesian equation of the curve and compare the Cartesian equation for the arc length with the parametric form and verify that in fact we get the same two answers. All right, have we got any other questions, Peter? What else do you... Brian?
No, we don't see any more questions coming in. There was something about how the duck's holding up, but
Okay.
about that one. Yes, that arc length one, Ray, I think that's particularly having the command on the calculator, that's going to be an absolute winner.
Yeah.
So the syntax there is basically the arclen with expression variable and then the start and end points.
Yeah,
I do
very
remember
similar
years ago a student asking me about that, a calculus student asking how could we actually work out the length along the curve, and we did a bit of research and found some appropriate formulas, but how neat that we can just do that as a command on the calculator.
Yeah,
all right, we haven't got any...
Following up from what Roman was saying before, is that if you try and do some of these calculations by hand, and I know in the workshops we did on Tuesday, a quick demonstration, and you can see how complicated the integration becomes, even for very simple equations that you would think would be fairly easy to work out the arc length, but they're not. So they're very contrived examples, and even the contrived examples can get out of hand very quickly. So I would think if it's going to be a by hand one, it might be something like set up the integral, or another one might be a scaffolded question where they get you to do it in 2 or 3 parts, because a lot of them you can use implicit differentiation to get to point A, and then so it might be show that the derivative equals, or show this, and then launch into an integration problem. But certainly, as you mentioned, is the arc length is very, very convenient.
Before we do move on, I just do have a question that's just come in, and it's asking, why use norm and not absolute value?
Oh, no, that's a very good one for length of things, like in vectors. And look, there's a lovely answer to that one, and that is when I do vectors and length in that context, I always get the students to use the recognition of the dot product. So if I've got a vector defined as A, then I'd get them to do A dot A and do the dot product and then just take the square root of it. And certainly if you do it as a generic one, in fact, and I know it's a little bit out of sequence, did you want to demonstrate that, Ray, or did you want me to do a quick demo of that?
You can do a quick demo of that one.
All right, then. Let me just drop in a new document if you want to transfer across to me. And this is what happens when you do things on the fly, isn't it?
Yeah, some of those commands that Ray's been using there, my students have been finding quite useful. The dsolve, the completing the square command for the standard form of circle. Impdiff has been another favourite.
Yep.
And Ray also did a presentation, another webinar on this a few weeks ago for exam readiness.
That's right.
So my students and I watched that, and thanks, Ray. We got quite a few good hints out of that.
So normally we would have something like the dot product of A and B, but if we do the dot product of A comma A, so doing the dot product with itself, then we can just do the square root of that dot product. Now, I kind of like that idea because it reinforces some of the things a student should be doing anyway, but if you want students to actually see it, I'm just going to change these back to variables. So if I do the dot product of A dot A, students can see very quickly that it's just x squared plus y squared, so therefore if I want the magnitude of it, then that's the definition for a magnitude of a vector. Whereas norm, as that person said, it's kind of just an out there command. It's not something we would normally have, and I think being able to do the absolute value of it would be a lot nicer. But we'll have a chat to the programmers with that one.
Yes.
Now, just before I go across back to Ray. I'll do a slope field one now. I don't want to throw things completely out of sequence for everyone, but slope fields have been on the course before. They're still on the course, and as Raymond's alluding to, and we did it in our workshop on Tuesday, is that there's a few differences in there. One thing I always found is that students didn't really understand slope fields very well, and we certainly see that from the examiner's report, is some of the questions which they should be able to do with very minimal effort, just plenty of understanding, students don't do quite so well. So what I did is I put together an activity, and I've still got to post this one up on our website, but all of these will be there in preparation for next year. Consider this one: a function has a property that the gradient at any point x, y is equal to half the y coordinate at that point. So on the next page, they've got a little slope vector, and we've got our y coordinate written there. So therefore, if I put my little slope vector there, then we could say that that's probably got a gradient of about 1. Or as Sheldon would say, exactly 1, if for any Big Bang fans out there. So the idea here is that students can then move that point and say, well, the slope of the function appears to be the same as I drag that along here. And if we think about what the literal description of our differential equation was, and that is half the y coordinate at that point. That's what our slope is. So therefore, because if I drag that horizontally, my y coordinate's not changing, therefore the slope is not changing. And then as I move it downwards, you can see that if y is 0, that has a 0 slope. If y is -1, our gradient vector is now showing us a negative slope, not as steep as what it is if I move it further down, and so on. So considering just one slope at a time at one point and aligning it strictly to the definition, then we're good to go. Students could write that using calculus. But the next thing that the activity says is to trace that. So I'll do a geometry trace of that vector as we move along. So we can see that the slope at all those y points is the same, or if I drag it up and down, and we're generating our own little slope field. But it's based on a very quick understanding of just considering one point in isolation. Now that's a very ugly slope field in terms of those vectors everywhere, but it does give students an indication of what that slope field means. The other one, and moving more towards, I guess, an understanding of Euler's method, and that is, here's problem number 2. A function has a property that gradient at any point x, y is equal to the negative product of x, c, and yc. So let's have a look. And this time, the point doesn't stick onto these the grid. It's quite flexible and movable. I've written quadrant 1, quadrant 2, etc. in the thing because the activity refers to those specifically. But in this time what we're looking at is moving along and following that vector. So let me just shift that label out the way a little bit so we can see our slope vector a bit better. So I want to actually follow it. So imagine my initial conditions were over here somewhere. I'm going to put him a little bit closer to the x-axis, or the y-axis rather. And this time when we trace it, rather than tracing the vector itself, I'm going to trace the point, and you can see I can trace vector or I can trace point. So I'll click on that one, and now as I move it along, what I want the students to do is just kind of follow where that vector is heading. And the gradient seems to be tapering off here. We get to 0 gradient, and I'm just kind of heading in the direction of the arrow. So as that arrow gives me an indication that the slope should be getting less, and now it says it's 0. Now, of course, the downside is it only allows me to trace so many points, but we're getting a rough idea of what that curve looks like. Now, if I put the vector somewhere else, in other words, gave it a different initial condition, then we would get a different curve. But what we've done is at least provided a set of points. And this is not completely different to what Euler's method does. My points are quite close together there, so it's giving us a general indication. So Euler's method is really saying, well, we need to head off in this direction, so the next point will be here. And once we get there, what does the new gradient function look like, or the differential equation? So hopefully that will give students a better understanding of what's going on. It's not new to the course, but it's one of the activities that we're putting up to try and help students understand. And in this case, we've got one that's dependent on both X and Y. So I guess in that context, it's kind of new to the course. All right, so I'll transfer back to Raymond. What did you have in store for us next, Raymond?
Well, I suppose I was going to quickly show them the arc length of the ellipse for the MCG and the Subiaco ground, but perhaps we'll let them work that out for themselves. I suppose what we should finish up with is everybody's favourite, the statistics section.
Oh, okay.
So let's move on to that. Do you want, while you've got it, do you want to do just Alex's little thing? And that will lead me into the confidence intervals and hypothesis testings.
Yep, certainly. All right, so what we're doing here is Alex has got his test result back, so I'm trying to give students a scenario that they can associate with, and certainly teachers can associate with it. But he's got his test back, and he wants to know, how did I go compared to everyone else? So he's got his score on the top of the test, but he actually wants to know, how am I doing in comparison to the rest of the class? So the teacher's particularly nasty and doesn't tell him, doesn't have to, I guess, so he decides he'll ask 3 of his friends and kind of calculate an average of that, and then he uses that to estimate the class average. Well, obviously a sample of 3 is not necessarily going to be a reliable estimate, but what I want to do is try and get across to students an understanding of the sampling statistic, so, or the sampling distribution rather. It's something that students haven't seen before, a sampling distribution, and I think that's important for them to get their heads around what that terminology means. So what I've got here is I'm going to replicate the question. We'll just reset our data. Now, the example doesn't fit specifically on the course in terms of the conditions because our population needs to be much larger than 2 or 3 classes of students. That's our population down the bottom here. And our sample size needs to be a lot bigger than 3, but it serves the purpose of getting an understanding to begin with. I wanted to be able to see individual points down here, and if I put in 200 or 300 points as a population, then we wouldn't be able to see that. So anyway, we've got the average of the population is plotted, and you can see once Alex has asked 3 of his friends, then he's taken that average. So we're looking at the average of the sampling distribution. And even though he's only taken 3 samples, it's still providing a reasonable estimation of the population mean. So I can click on here and take a second sample. So he's not satisfied with the first group of friends that he's asked, so he's run off and asked 3 more of his friends, and he's put those 2 points here. So that was the result of one sample, that's the result of another sample, and looking at the mean of those 2 means, it's still relatively close. So he decides to badger some more friends, and some more, and some more. So now he's taken, what's our 5 samples of 3 students. And we can see that we can start to plot those points, those averages. And the more samples that we take, the closer we actually get to the mean of the population. And you'll see that as I take more and more samples now, that mean of that sampling distribution, these red dots are my sample distribution, this is the population, and these are all of my samples. So you'll see from now on, this mean of our sampling distribution will pretty much sit right on top of the mean of the population, and that's one of the first things that students need to understand. The other thing which is interesting here is these 2 points down here. So they were means of 3 students, or 3 scores that he took from the population, and you can see they're actually quite low, so it's quite unlikely that these 2 samples are going to happen. It's possible, of course, and we've got another extreme point up here. It's highly unlikely that we'll actually get a point down here. So we'll continue to sample. In fact, we can animate it, and it will sample so that I can talk rather than clicking buttons, and you can see our sampling distribution has a mean pretty much the same as the population mean, and that it's starting to appear approximately normal, which is kind of what we'd expect, and that's what the whole premise is based on. The sampling statistic has a normal distribution. In other words, we're now starting to talk central limit theorem, and it has a mean equal to the population mean, and the standard deviation, it doesn't seem to be spread out as much as the population. So let's just stop him sampling there. He's annoyed enough people. And what I'm going to do is change the number of people that he asks. So his sample size is now 10. So we'll reset the data. So he's asked 10 friends, and that's his mean. He asks another 10 friends, and you'll see this time how quickly the two means align. And from now on, we get very little variation in that sample mean. We'll animate it. But you'll also notice that we don't get the points down here, because now it's almost impossible to get points all the way out here once we start sampling off 10 people, because we're unlikely to get the 10 lowest scores from our population. And from that, students can see almost instantly that the standard deviation of the sampling mean, or the sampling distribution rather, is affected by the size of the sample, and that's what Raymond will show us in a moment in terms of the actual formulas that students need to use, and that we're still getting something which is approximately normal. So we can see that sampling size is important. It affects the standard deviation of the sampling distribution, and that the mean of the sampling distribution is approximately the same as the mean of the population. So I think the one little demonstration is giving students a fairly good insight into the sorts of concepts we want them to have. And the study design actually refers to understanding and doing simulations. And we can see there that's our sampling distribution, and we've fitted an approximate normal distribution over the top of it. So that I think is a reasonable example, and that one will be up on our website as well when we finish working on that website.
So with that, beautifully illustrative, isn't it?
It is, and I think the context is something which students will appreciate, because it's the sort of thing they naturally do when they get a test result back, unless, of course, that they're this student down here and they know that they got the lowest score. The ones around here and up here do tend to run around asking their friends, how did you go, how did you go?
Yes.
So it's something they naturally do.
A couple of things though, Foxy. I'm just wondering, is the mean of means no average feet? And also...
That's very clever.
Thank you. And also, if I've only got 2 students in my class, do I do a sample of 1 and then a sample of 2? I think that would probably do it.
Well, I think we'd have to extend it out, and I think if you've got a specialist maths class of only 2, then there's at least 20 or 30 other people on this webinar that would probably like to reach out through the phone and strangle you, particularly if that forms a part of your allotment, because some of them, I know some of the people that are on the webinar have very large classes. I know I had one of 27 students one year, and that was hard work. So yes, it's something that you would want to be very careful of at the MAV conference this year, Brian, is that those people may come and strangle you under the understanding that you only have 2 students in there to work with. Yes, but look, having said that though, I know when I've had smaller classes, the amount of work you put in is still the same. You have less corrections, of course, but I find the classroom dynamics are completely different as well. It becomes more of a tutorial, because you feel like a bit of a ning standing at the board writing things down. Yeah,
it makes it much harder for students to bounce ideas off each other.
Yeah.
In previous years when I've had more, they've actually been collaboratively constructive.
Yes.
In their problem-solving approach.
That's right. All right.
So I'm looking at time here as well.
Yep.
We're at about 9 minutes to wrap up.
Yeah, so I'm going to send it across to Raymond, who will go through the actual calculation. So that's the simulation that is useful to get the understanding, but students still need to be able to do the calculations. Do you want to share your desktop there, Raymond? And hypothesis testing as well. Now, that's one that people haven't done much of before, unless they've perhaps been teaching IB, which is a good source of questions if people want to use that. The other one that I'll see when Raymond demonstrates it is that you can use raw data as well. You don't just have to provide the stats from your sample. You can have the sample as a list and do the hypothesis test on that. So we can see Raymond's desktop. So for it.
Yes.
All right, now the final news section for the specialist maths is this statistics stuff. The sums of random variables and confidence intervals and hypothesis are the three basic topics that we're going to quickly look at in the last couple of minutes. The linear combinations, that's sort of been in the methods course for quite a few years. These sort of formulas are directly from the study design, so we won't go through them. We won't go through this example. What we'll go through is the central limit theorem, which is basically what Peter was talking about, that the sampling distribution x bar has an approximately normal distribution, and provided n is sort of large enough, then we get a narrowing in. So the standard deviation is now sigma on root n, and this is also called the standard error of the mean. So this is the CLT. Everybody knows what a BLT is, don't you? Peter, you're going to do it again for me?
Yes, so the CLT is the BLT for vegetarians, where they've substituted bacon for carrot.
That's the central limit theorem. Yes. The whole point of this statistics area here is that we really don't know the mean of the population, and we use different symbols. So mu is the mean of the population, sigma is the standard deviation, or sigma squared is the variance of the population, and x bar and s are the means of the samples, etc. So what we want to do here is just have a quick look at some hypothesis testings. Now, hypothesis testing and confidence intervals. The confidence intervals are also sort of in the methods course. So basically when we look at what's called a confidence interval for the mean, basically we're using this sort of horrible terminology, ZL for on 2. It's just the values for which we're within a confidence interval. So we're talking about a standard normal distribution, 0, 1. The magic numbers here that we really need to know are the 99, 95 and 90%. So 95 is 1.65, 95% is 1.96. Now in further maths people know that two standard deviations are approximately 95%. It's actually 1.96. So we're using 1.96 and 2.576 for 99%. So they're my values of alpha. So basically what's happening in here is that we've got an unknown mu. So if we look at this, x bar minus mu over s over root n is modulus of that's between z alpha on 2, which means between minus z alpha on 2 and z alpha on 2, we have x bar minus mu over s over root n. What we want to do is transpose that for the unknown, which is mu. So the whole point of doing a confidence interval is just to work out x bar plus or minus z alpha on 2 times s on root n. We're actually approximating s for the standard deviation of the sample rather than the population. All right, so let's just quickly look at an example here. An electrical manufacturer manufactures light globes. They've got an approximately normal distribution. We take a 25 samples and we find that the average lifetime is 780 with a standard deviation of 40. We want to find a 95 or a 99% confidence interval. Now, the fact here that we've got 25. 25 is sort of the value in statistics where we can say small. Anything under 25 for n would be small. Anything above 25 is sort of large. So we're really using z values here. So let's just have a look at how we can actually do this on the calculator. So let me add a graphs page. If I add a graphs page, a calculator page here, and we want to do some statistics. So let's hit the menu command. What are we doing? We're doing statistics, yes. We're doing confidence intervals, so that sounds pretty good. So come down to number 6 here. And there are t intervals. Now the t interval is when we've got values less than 25. We're only using z, so we're using a z interval. Now data method. As Peter was saying, if the data, you've got the data in a spreadsheet, then you've got the data. You'd actually have to have 25 lots of students' data to do this. We don't have the data. We actually have the stats. So let's choose the stats. Now, once again here, we're approximating the standard deviation of the population here. So sigma from the example was 40, x bar, the mean of the sample was 780, n, the number of values was 25, and we could choose the confidence interval to be 95 or 99%. Simply tab to OK, and there we've got the results. We've got the lower extreme and the upper extreme. So this is a Z interval. Repeating that for 0.95 or 0.99 would give me the result for the 99% confidence interval. So a confidence interval is very, very easily done. All right, so hypothesis testing. Now this is a fairly broad area, can get a little bit complicated, but again what we're doing is gathering information about the population parameter based on the sample. We actually have to form the null hypothesis, which is what we assume it to be with no problems. And the alternative hypothesis can have three different forms here, either a not equal to or a one-sided test left or right, greater than or less than. So the various steps are to calculate the statistics and then work out whether we're actually in my acceptable region or not. There are a number of errors that can actually happen here, and these little questions would be good multiple choice questions defining what's called the type 1 and type 2 errors here. Let's just look at, this can also be offended to a court of law where we actually have the type 1 and type 2 errors. All these files will be available to you, so we'll leave them up that you can grab at a later stage. So let's just show how we can do a hypothesis test on the calculator. Cereal packets are meant to contain 500 grams. You know, you read on a packet of Kellogg's cornflakes, it says average contents 500 grams. To check this, someone actually weighed 100 packets and showed that the mean of the sample was 497 grams and the standard deviation was 20. From this information, do we have information to say to the manufacturer that you're actually underfilling the packets? Now, at first stage here you might think, well, yes, 497, but the fact that there was 100 packets there. So let's just show how we can actually do a hypothesis test on the calculator as well. Once again, very easy to do, but the calculator gives us results. We still have to interpret the answers here. So that's a good thing. It doesn't actually give the answers. You still have to interpret what's going on. So once again, we go to our statistics menu, and last time we went to a confidence interval. This time we're actually going to do a statistical test. Now once again, it's the same sort of thing. We're doing a Z test, not a T test. We'd use a T test if we had less than 25. So once again, we don't have data, we've got the stats. So tab to OK. Now, what is mu naught? Mu naught is what we think it was. So we think that everything is going to be OK. So we're thinking mu naught was 500. The standard deviation, what was the standard deviation? The standard deviation was 20. The X bar, the mean of the sample, was 497. N was 100. And notice that we've got three choices for the alternative hypothesis here. It was a less than, or a greater than, or not equal to. So we'll choose the less than. Tab to OK, and there we have our results. Now, we can also interpret this from the p-value, which is the probability that it's been happening here. So 0.068 is fairly large. It's not under our 0.05 or our 95%. Generally, you'd probably do these at, say, 95 or 99%. So we have to interpret the results here. And an interpretation of the results here is that we really don't have evidence that the manufacturer is underfilling the packets. Now, it's a simple little Z test, but the calculator does a Z test and a confidence interval quite nicely. So I think at that stage I'll hand it over. Remember again, the new topics, the confidence intervals, hypothesis test, arc length, DEs, rays, lines and circles for complex numbers, more integration, more formulas for sketching graphs of rational type functions, are basically the new areas for the specialist maths for 3 and 4 next year for 2016. So at this stage I'll hand it back to Brian. Any other questions we've got, Brian?
Yeah, there was one that I saw. Sorry, I jumped in, Brian, I'm just watching the time, is in relation to t-tests. The study design, which I have open right now, refers specifically to normal distribution, not t-tests, and that's one of the reasons why we've got to have n greater than 30 as a rough guide. certainly one of the things, and this is something we discussed on Tuesday as well, is that if you wanted to, you could show students, if you want to be more of a purist, is that the T distribution approaches a normal distribution as n gets larger, and 30 is not a bad point. It's not a hard and fast rule. It's a rough guide. It's a bit like a 95% confidence interval, and it's an accepted point. It largely depends on the distribution itself. If the original distribution is binomial and P is approximately a half, then 30 is a good indicator. So we don't do t-tests in the specialist course. It's only Z, or a normal distribution, and therefore they have specifics on it with a known mean and so on. So t-tests are not in the specialist maths course.
Okay, thanks Peter, and thanks also Ray, and to participants for joining us this morning. As I promised at the start, you were due some terrific activities and ideas there, and I might remind you to take a look at the teacher resource section of the TI website, where we're posting more and more of those activities. Australian Curriculum Inspired is a wonderful source of activities, and I think with that expanding to focus especially on the new VCE courses, that will be even better. So just in the wrap-up, a reminder that coming soon to an email address near you will be your PD certificate for today. Also, copies of the files and things that have been demonstrated here. After the webinar, we would appreciate your feedback, please. So when you sign out, your computer screen will go to a feedback page. That'll only take a minute or so to complete. So we would appreciate your help on that. And I've mentioned you will be getting that email soon. Just a reminder of our products and services. There's the Student Centre. There's the YouTube channel where a lot of these ideas are illustrated as well. And of course, there's more PD opportunities, whether that be through webinars or through face-to-face events. So the first point of reference for all of these things is your Texas Instruments website. And just a reminder on the webinars, if you want to see more of the type of thing we've been doing today, first of all, Peter and Raymond, I know, are running a session similar to today's at the MAV conference in December. Also, later on today, coming up at 11:30, Russell Brown and myself are looking at what's new in the general and further mathematics courses for next year. And later today, Russell is joining with Peter Flynn to do the same sort of thing for the Maths Methods course, and that's at 2 o'clock. On the webinar link in the website, you should also take a look at the on-demand section, where in probably 48 hours' time you will be able to download the full video of the webinar that you've just participated in. So you'll be able to replay it and pause it and take notes, etc., at your leisure. So in wrapping up today, thank you to both of our presenters for excellent presentations, and thank you to all participants.